So we're going to be covering several things. So the first major topic here is discrete random variables. So we're going to deal with the binomial, uh, the geometric random variable, and the Poisson. So those are the three main discrete random variables that will be tested. Number two, of course, is the continuous random variables. In particular, I want you to understand the probability density functions, and then specifically uniform random variable, exponential. And then I made the normal distribution its own thing because there's much to say. There's much more to say about the normal distribution than the rest of the random variables. Then under the normal distribution, we have things about the standard normal, applications of the normal random variables. So it's more word problem based. And we're going to use the normal distribution to approximate using continuity correction binomial random variable. So, and the last thing here is expectation and variance. So all of this will be covered for your exam number 2. Okay. All right. So there's a lot of, as you can tell, there's a lot of problems to choose from. So if anyone has a particular place they want to start, do you guys want to start with discrete random variables first, continuous random variables, or something else, expectation and variance? Does anybody have any, I would say, any preference? Geometric random variables, yes, of course. And the way usually these questions are structured, right? The first few, the first problems are usually like the more basic ones, and then it gets more complicated as you go. So let's look at the first one here. Let me just. Okay, so here we are. We have a geometric random variable with parameter 0.2. Find the probabilities below, and we have 3 different probabilities. So let's look at the first one. So one major piece of advice for this particular exam is to go through all of the random variables that I've just delineated that's in your review sheet, and go through every probability mass function for the discrete random variable, and go through and review every probability density function for all the continuous random variables, and also know the expectation for each of those random variables. So for example, here, the big key word here, or key phrase, is geometric. Now, if you don't know what a geometric random variable represents, that's something you have to cover. And if you don't know what the PMF is, that's another thing. So does anybody recall, what does a geometric random variable represent? Number of times, yes. The number of times it takes to get the first success. That is right. So this represents the number of trials until first success. So what am I saying here? This is the probability that my first success occurs on the third try. So if it occurs on the third try, if it comes on the third try, then that means that the first two tries must have been failures. Now the parameter P is the probability of the success. So that means that the probability of failure, which is usually defined by Q, is going to be 1 minus P, which is 0.8. So the probability of getting my first success on the third try, so this is the first means that I must have had 0.8. I must have failed, quote unquote, the first two tries, and then I must have uh, succeeded the third try. And so this is going to be my probability. So you can compute that 0.8 squared times 0.2. And I get 0.128. Okay, that's part A. And I just want you to recall, what's the PMF of geometric? So what is the PMF? Remember, the probability mass function is the way we compute the probabilities for each value of our random variable. So our random variable x can be several things, call it k. Now, what is this representing again? This is representing what? This is the first success on the what try? On the kth one, right? On the kth try or attempt or trial. And then that means that if you found your first success in the kth trial, then you must have failed the k-1 trials beforehand. So then that's why you're going to get the with the parameter. So PMF of geometric with parameter. That's another thing that you must know with parameter P. You must know for each random variable, whether they're discrete, right? You should know the PMF. If they're continuous, you should know the PDF. You should know the expectation for each random variable, and you should also know the parameters associated with each random variable. Each random variable has a different set of parameters. For example, the geometric random variable really only has one parameter, and it's P, which is the probability of success. And then this is going to be 1 minus P to the k-1 multiplied by P. And this is for k equaling 1, 2, dot, dot, dot. Okay. So part B, what's the probability that x is bigger than 8? What does this mean? Now, this is a little bit different, right? It's not an equal sign, it's a greater than symbol, and this is for discrete. So what does x being bigger than 8 mean? 1 minus x less than 8. Oh, I see what you're saying. You're going to do complementary counting? Yes. So, but what is this saying though here? It's saying that the first success occurs after uh, eight after 8 trials. So it's saying it takes more than 8 times to get the first success. That's right. Right. So it could be the ninth try, it could be the 10th try, it could be the 1,000th try, it could be the a millionth attempt. So it's saying what's the probability that that occurs, that the first success occurs after 8 trials? So how would you compute that? I think, and I think that's what Alexandra suggested. Do 1 minus the probability that x is less than or equal to 8. Now we have to say less than or equal to because x greater than 8 means that your x equals 9, 10, 11. So if it's the complement of x being greater than 8, then it would be less than or equal to 8. Now, how do I compute this? 1 minus this. What is this? Yeah, we're in the discrete world, so that's how we take care of that complementary aspect of it. So I should just highlight that this here is the complement. Okay. So how do we compute the probability that x is less than or equal to 8? CDF, that's right. This is, well, it's, yeah, that's right. It's CDF. So how do you compute the CDF for a geometric random variable? So the idea, right? The idea is that I'm calculating this, the probability that x equals not 0, but 1, then plus the probability that x equals 2, plus all the way to the probability that x equals 8. Which is 1 minus, and then this is going to be p plus, this is 1 minus p times p plus p, pardon me, 1 minus p squared times p all the way to 1 minus p to the 7th times p. And what do you recognize? There's a whole bunch of p's, right, that you can factor out. So this is 1 minus p, 1 plus 1 minus p plus 1 minus p squared plus dot 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 all the way to 1 minus p to the 7th. But we already know what p and 1 minus p are. This is 1 minus, this is 0.2, 1 plus 0.8 plus 0.8 squared plus dot 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 plus 0.8 to the 7th. And yes, I just want to make that clear. This is the CDF. So you can do this many ways. You can put this in your calculator, like straight up this way. But you can also, in your calculator, utilize the distribution. So if you go to second vars and you go all the way down, you have the geometric CDF. So you can compute that. And hold on. I think I made a tiny mistake. So this second vars, then geometric CDF, then the p-value, which is the only parameter that we have, is 0.2. The x value is up until where we stop at, which is 8. And I get 0.83222784. And just to make sure that the computation we were doing earlier is okay. I'm going to multiply this by 0.2, and then I'm going to find the summation of this. So I'm going to do a summation, and I'm going to say x equals, put 0 to the 7th to 7, and this will be 0.8 raised to the x. So the idea is that I encapsulated the sum 1 plus 0.8 plus 0.8 squared plus all the way to 0.8 to the 7th with that. And I think something's wrong with the setup here. But let me see. Yeah, I think, hold on. I'm just gonna do it the old school way. So I'm gonna get 1 plus 0.8 plus 0.8 squared plus 0.8 cubed plus 0.8 to the 4th plus 0.8 to the 5th plus 0.8 to the 6th, and then finally plus 0.8 to the 7th. Yeah, you do have to multiply by 0.2. That's why I'm putting the sum around with parentheses. So it's distributed. That 0.2 is distributed. And do you see how we get the same number as the CDF? So what we calculated here is the CDF of the geometric random variable. The reason why the summation here may not be working is the x value itself, that symbol x may not be the best index. So I would have to use some other letter here. So that's maybe why it keeps coming up with 0.2. But in any case, this is 0.8327. And then you do and then you do 1 minus 0.83222784. And then when you do that, so you do on your calculator, you can simply say 1 minus the answer, 1 minus the answer, and you get 0.167777216. So this is going to be the probability that your first success occurs after 8 tries. And there's another way you could have also interpreted this. The probability that you could have also considered it as if you have to take more than 8 tries for your first success, that means that your first 8 tries should have been failures. So that's another way to consider that. So that means that it must have been, what is it, 0.8 to the 8th power. Let's see if that, do you guys see that? If you do 0.8 to the 8th power, you would get exactly 0.167777216. You get the same thing, but it's just, look how much less computation it is than doing all of this. This is the more straightforward, direct way, right? This is direct line of reasoning, utilizing the PDF or the PMF of a geometric random variable. But this is more thinking about what the event you're finding the probability of is. You're saying that the first 8 tries must have been failures. That's the equivalent statement to this. First 8 attempts are failures. That's another way you could have thought about it. Okay, so any questions about parts A or B in this problem? No. Can we do 2.1 number 1 next? Sure. But let me just finish part C here. Part C says the probability of 5 less than or equal to x less than 13. No problem. What does this represent? This represents the PDF, right? When x equals 5, PMF, pardon me, when x equals 6, all the way when x equals 12. So again, you can do the whole 1 minus p to the 4th times p plus 1 minus p to the 5th times p plus 1 minus p to the 11th times p. And you would have noticed that all of them have p's in it. So you get 1 minus p to the 4th plus all the way to 1 minus p to the 11th. And you just plug in the p being 0.2 and 1 minus p being 0.8, and then put that as a calculator. Put that computation in your calculator, or we can utilize our calculator. How can we utilize our calculator to help us find this a little bit more simply? Given the fact that we have a calculator that computes the CDF, how does the cumulative distribution function here help us find the probability of this? Does everybody see what I'm asking? So you see how we're finding the range in between two numbers of the probability? Right, Ethan. So something like that, right? The CDF of 13. Well, actually, so this is always have to be careful because this is a discrete random variable. So when x is less than 13, it's like saying x is less than or equal to 12, right? So equivalently, this is the same thing as saying the probability that 5 is less than or equal to x, which is less than or equal to 12. It's the same thing. Being less than 13 in the world of discrete random variables is the same thing as saying less than or equal to 12, right? So that's why the less than symbols here, they matter a lot, whether it's less than or equal to or less than or strictly less than or strictly greater than. It matters a lot in discrete world. In the world of continuous, not as much, right? not as much, because this here would be the same thing in discrete in continuous rule. It would be the same thing as um x less than or equal to 13. These are the same, but in discrete world, these are not the same. These are not the same. These are the same in discrete world. So it's a little weird, right? But regardless, what we can do is we can take the probability when x is less than or equal to 12, which is the CDF, right? The CDF minus the probability that x, in this case, not that it's less than or equal to 5, but less than or equal to 4. Again, understand why. Why do we do that? Because the PDF here relates all the values when x equals 12 all the way when x equals 1. So this is x equals 12, x equals 11, all the way to x equals 1. But I want to take the ones that I want to leave 5, but I want to take everything less than 5. That's why I have to take away x less than or equal to 4. So then I can do that in my calculator. I do second vars. So CDF. 0.2, the x value here would be 12. Paste. And then subtract that from the second vars. CDF. 0.2, and this will be 4 instead. So you see, I'm subtracting the PDF from 12 of when x equals 12 all the way down, and then getting rid of the values when x equals 4, 3, 2, 1. So that should give me everything in between 12 and 5, including 5. So then I get 0.34088 dot dot dot. And then you can also verify that yourself if you just want to find it directly using the original approach, which is without the CDF approach. You can also verify if this is the same, and it will be the same. So if you just use this idea here and just straight up plug in 4, 5, 6, all the way to 11, then this number, this expression, the value of this expression should be the same as this value. Okay, so this is an example of geometric random variables. So any questions about this? If not, we can move on to the next one, 2.1, number 2, right?
Hi, Professor. I have a question.
Yes.
Okay, so to get the full credit on like the exam, like so let's say like I calculate the geometric CDF using the calculator rather than trying everything. If you want to get the full marks on that question, do we need to write everything like this, or what exactly do you want on that?
Yeah. Write out everything as much as possible. So if you use, for example, your calculator, right? You want to use your calculator for this. So you can simply use say I used the calculator. I used a CDF function on calculator. For this particular step here, you don't need, if you like, all of this is not necessary for this particular problem. I could have went from here and went straight here. I'm just showing you. Yeah.
So I can just write the px less than or equal to 12 minus px and less.
Yeah, you could have,
and then just write the answer.
You could have went from here to here. No problem. What I'm just doing it, like, from my perspective, is I'm showing you all different ways. So this is one way of doing it. This is just like straight up one way of doing it. But then I'm like, of course, you start seeing that this is kind of unnecessary to compute every single term and then add it. You could do that. I'm just saying it's not necessary. Another way to think about it, as some students have suggested, is, hey, consider the CDF minus the other CDF. So this here gives you this probability. And then computing this, of course, the point of making the CDF here or noting that this is a CDF is you can compute that using your calculator. And from this step here, I understand what you're doing. If you don't
Mm-hmm.
put this, then I don't know what you're doing.
Okay, so you just need the this thing, and then I can use the calculator, and I can get full marks.
Yes, you would
Okay.
get full if you show me and just look, it doesn't hurt if you just put everything as much as you as be as clear and as um detailed as possible. So the more clear and detailed that you are, the less possibility that there is going to be, oh, you forgot one little thing here. But yes,
Uh,
for this particular problem
it's for
here,
the like time saving, so I was just asking for.
oh, of course, I know time is of the essence, of course, of course. But like I said, the more detailed you are, the less likely you are in losing anything. But for this problem for here, you can go from here to here. Just
Mm-hmm.
say, hey, I use my calculator. Just I use the calculator to find the CDF. And then you get the numerical answer. Same thing here, right? You don't have to do all of this.
Mm-hmm.
You could have also went from here to here. I recognize, oh, I know what you're doing. CDF, it's the CDF. So you can use the CDF function in your calculator and went straight here. Boom, boom. Or really nicely, you could have just done this, which is even more compact. And
Uh-huh.
yeah, but
Yeah,
like I
sure.
said, as much as be as detailed as possible. Okay, so the next one, um, let's see. The next one is 2.1, number 2, right? So we're doing this one here. Okay, so here we have a random variable. It's a PDF, so and immediately the way it's written here, we know it's a continuous random variable. And so we want to find a constant c, and then we want to find the probability that x is bigger than 2, 3/2. Okay, so how do you find this constant c? Well, we know it's a PDF. What's a mandatory requirement for a PDF of any continuous random variable? Something about equaling 1, right? The integral from negative infinity to infinity of my PDF must be 1. So this is a mandatory requirement for the CDF for any PDF. So this one is no exception to the rule. So that means that my function here, so from negative infinity to infinity of my probability distribution function, it should equal 1. But if you look at the way it's defined, this is defined between 0 and 4 and 0 otherwise. So outside of the values for x being 0 and 4, your probability density function is 0. Within that interval, it's cx squared. So that means that this becomes 0 to 4 of cx squared dx. This must equal 1. Then what you can do is you can factor out the c, and this is 0 to 4 of x squared dx. This must equal 1. But then this here is a integral that we can, definite integral that we can integrate and compute the value of. This becomes x cubed over 3 from 0 to 4 times c equals 1, right? So when you plug in, when you evaluate this definite integral, you get 64 over 3 minus 0, right? Times c equals 1. So what does c equal? The constant value must equal 3 over 64. So that must be c. So then the PDF f of x can now be written as 3 over 64 x squared when x is between 4 and 0, and it's 0 otherwise. Okay? And then how do we do part B? I want the probability that my random variable is bigger than 3 halves. So how do we set this up? Again, in the world of continuous random variables, probability is area. And area underneath what? And it's the area underneath the PDF. So what I'm saying here, the probability that x is bigger than 3 halves, I'm saying find the area underneath the PDF from 3 halves to infinity. That's what I'm saying. This is by straight definition. The probability of a continuous random variable being bigger than 3 halves is equal to the integral of my probability density function from 3 halves to infinity. But of course, this particular PDF, right, is 0 beyond 4. So this integral must be between 3 halves and 4. And I know my PDF is what? It's 3 over 64. That's going to be the continent outside of x squared dx. So now this probability question transforms itself into a Calc 2 integration problem. And then we can compute this. So this is 3 over 64. This is x cubed over 3 from 4 to 3 halves. So this is 3 over 64. 64 over 3 minus, this is 3 halves cubed over 3. (64 over 3 minus 3 cubed is 27 over 2 to the third power is 8. So 8, this becomes 24 in the denominator. And then you can multiply the top and bottom by 8. And what you get is 64, you get 512. 512 over 24 minus 27 over 24. And then 512 minus 27 is 485. So this is 3 over 64 times 485 over 24. 3's here and the 8 here cancels. This becomes 485 over 64. 512. So if we're finding a range for x, like a 2.1 number 1 part B, we would just replace the bounds and this with the range asked for and solve like this. That's right. That's right. That's what this stuff is. Yeah, I know, right? So this is awesome because I feel like now maybe you can see the significance, for example, of learning why you integrate. This is one reason why you learn the the usefulness, the utility of integration. Um, and hopefully this starts to clarify maybe certain ideas of mathematics, right? Because a lot of people always ask me the same question. What's the point of doing this? What's the point of learning this? What's the point? What's the point if I'm never going to use it? But the thing is, you never know. And a lot of these things that you learn are very rudimentary. So that's the reason why you don't see the usefulness because they're very basic things. Integration is a basic mathematical technique. It's a fundamental, I should say, mathematical technique for such things such as this, finding the probability, which is can be extremely applied um, endeavor. So the probability of these random variables are calculated by integrals. So you need to know how to integrate in order to find or compute the probabilities. So yes, to your question, Alexandra, for number one, it's the same procedure as part B and number two. You are just utilizing the um, given PDF and setting up so this here this the direct definition of this would be the integral from 1/2 to negative infinity of f of x dx. Why am I doing that? Because my x value has to be less than 1/2, and my x value, my random variable x is a continuous random variable, and the continuous random variable are the values of a continuous random variable go from negative infinity to infinity. So when I'm specifying this, I'm saying x values has to be less than 1/2, so it has to go all the way to negative infinity. But the way that my probability density function is defined, my x values can only be between 0 and 1. So then this here becomes this. Okay, so this always depends upon what the PDF that you're given. All right, so this would be the final answer here. Of course, you could put this in your calculator and get the numerical value, decimal version if you need it. That's right, Alexandra, that's right. So for exponential, because if you remember what exponential looks like, so that's why I told you, I've mentioned in the beginning that for this particular exam, you should be studying and clearly identifying the PDF for each continuous random variable and the PMF for each discrete random variable. So for exponential, you must know that this is lambda e to the negative lambda x when x is greater than or equal to 0 and 0 otherwise. And by this otherwise, I mean x less than 0. So if I want to find the probability, for example, x being greater than 1/2, or I should say, let me say less than 2, for example, right? This would be the integral from negative infinity to 2 of the function dx. That's by direct definition of the probability of a continuous random variable. But because the PDF of this continuous random variable is only defined uh, as a non-zero value when x is greater than or equal to 0, then this integration bound is updated or set up where the lower bound must be 0, and this would be lambda e to negative lambda x dx. Yeah, this negative infinity is just, this is purely, if I didn't even know what f of x was, even if I didn't know what this was, the way we define the probability of a continuous random variable being less than a number or greater than a number, right? Particularly less than a number, is that we're saying inherently, even though it's not written, what I'm saying here is x is less than 2, but greater than negative infinity. That's really what I'm saying. Every single time I write x less than 2, that's what I'm really saying. But we don't write is greater than negative infinity. We don't write that because it's implied here. It's implied. But anyways, okay, so I'm glad things are starting to click and clarify themselves when you solve these problems. That's the whole point. The whole point of these problems that I give you is that I hope by solving them, you start to clarify any misunderstandings you may have. It just solidifies your understanding even further. So that's good. Okay, so that's number two. Any other things? So we've covered geometric and we've done PDF. So now it says 2.3, number 4. 2.3, number 4. Okay, so again, this idea of exponential, that's very important. We have to understand what kind of random variable we're dealing with. So we're dealing with an exponential with an average life of 1 year, so that lambda is 1 over 365. So the length of life is defined by, so let's just write this. X is the length of life in days of an alkaline battery. It has a exponential distribution, and we know that lambda is 1 over 365 because the expected value is 365 because it's in days. So this is 1 year. And remember, the expected value of a exponential random variable is 1 over lambda. So that's why lambda is 1 over 365. Okay, does everybody follow that? Okay, sure, no problem. So that's the setup in the beginning. Now, part A asks, what's the probability an alkaline battery will fail before 180 days? So how do we write that? How do we write part A? A lot of this is just writing from words to mathematical notation. That's the hard part. And then beyond that, it should be more straightforward. But what's the probability that an alkaline battery will fail before 180 days? How would you write that mathematically speaking? Well, X is the length of life. And I'm saying that the length of life is less than 180, right? So this is the same thing as saying the probability that X is less than 180. That is exactly what this means. What's the probability that the alkaline battery will fail before 180 days? What's the probability that the length of life, X, is less than 180? And then we use this, right? The integral from negative infinity to 180 of f of x dx. But what is f of x? This is what? Exponential. We just discussed this. This is lambda e to the negative lambda over x, right? So this should be 1 over 365 e to the negative 1 over 365 x when x is greater than or equal to 0 and 0 otherwise. Again, this is the PDF of exponential. So then this will equal the integral from 0 to 180 of 1 over 365 e to the negative 1 over 365x dx. This is 1 over 365, the integral from 0 to 180 of e to the negative 1 over 365x dx. And then you can take the antiderivative of this, which becomes negative 365 e to the negative 1 over 365x evaluated from 0 to 180. When you plug in 0, when you plug in 180, you get negative 365 e to the negative 1/2 minus, and then the minus becomes a plus because of the negative. This becomes 365. Yeah. And then you can take out the 365. And if you factor out the 365 from both, and you multiply by 1 over 365, that cancels. And what you're left with is 1 minus e to the negative 1/2. That is the probability that x is less than 180, which numerically will be 1 minus e to the negative 0.5. So rounded to the nearest 4 decimal places, 0.3935. Okay. Any questions about this? What do you mean, Ethan? Isn't it a little less than 1/2? 18. Oh, you're right. You're right. You're right. You're right. You're right. You're right. I meant I just went straight up. You're right. I thought it was 360 for some reason. This should be 180. That's right, Ethan. This is 180, negative 180 over 365. So this should be negative 180 over 365. So yeah, it's going to be slightly less than 1/2. I see what you're saying. So if I rewrite that, it's going to alter the answer a bit. Well, did it really alter it? Yeah, it did. This became 3893. So that should be correct. So thank you, Ethan, for pointing that out. Alexandra, you're okay. It looks like I don't know if that's a nervous thing or again, this stuff here is strictly Calc 2 integration, which I expect you all to know how to integrate. The real issue here is just setting up the problem here. And then what would be part B? How would you write part B? Part B is saying what is the probability that an alkaline battery, typo there, battery will last beyond 1 year? So then how would I write that? That's right. So P is bigger than a year. Like X is greater than a year, so X must be greater than 365. Now what is this going to be equal to? Well, it's equal to the PDF with these integration bounds from infinity to 365. So this is 1 over 365, 365 to infinity of e to the negative 1 over 365x dx. And so this equals 1 over 365 negative 365 e to the negative 1 over 365x evaluated at 365 to infinity. And when you're evaluating an improper integral like this, normally we write this as a limit of negative 365 e to the negative 1 over 365x minus plus 365 e to the negative 1. But if you notice, this is an exponentially decaying function. So as you go to infinity, this whole thing goes to 0. So this goes to 0, and I'm left with 1 over 365 multiplied by 365 becomes 1. So the answer is e to the negative 1, or 1 over e. So it's approximately 0.3679. Everyone okay with this? Does the constant always cancel? I will never say that it always cancels. Does it always cancel for exponential distribution? Yeah, you have to be careful with that if it always cancels. For these particular examples, it does. And I would venture to say for exponential distributions, the lambdas, when you evaluate this, tend to cancel. They tend to cancel out because of the way the PDF is, right? It's an exponentially decaying function. So when you do the antiderivative, the lambdas will cancel out. But if it always cancels out, always be mindful of that word always. Does it always cancel out? Doesn't always, but most of the time. At least for the exponential distribution, yes, it has canceled out. Okay, and so I remember, I don't know if you guys, when you guys learned about the Euler's constant, the Euler's number, they would always say that it's more, there's more to talk about than pi. Pi is normally just used for circular shapes, right? The area, circumference, and the like. But the interesting thing about E is that it's found in nearly in unexpected places in mathematics. So it's found in differential equations all the time, and then it's found in probability a lot, and compound interest, and all this stuff. So E is very versatile and diversely applied constant, a bit more than pi is. Okay, so then any questions about number 4? If not, we can move on to something from 4. So Alexander says something from 4. Are you referring to expectation and variance? Yeah. So does anybody have any other? So like I said, there's a lot of here to choose from. There's normal random variables, which is a very important, that's why its own section, a very important random variable to deal with. Uniform. I've done a little bit of PDF, Poisson, binomial. Yeah, we can do something in number 4. It's a bit number 4, section number 4 is a bit of a melting pot of things. So you have problems where you're given the expectation and variance, and then you're finding the expectation and variance. We've done a lot of these, I would say, right? In homework. Number four of number 4. Oh yeah, so see, number 4 of number 4, that's a more interesting one. This is nice. So here we have density function of x is given by this strange uh, function here, the PDF. What they do tell us for part A, they tell us that the expected value is 3/5. Now, this is very interesting. Normally, they ask you to find the expected value, but this time they're telling you. It has the var x as well if we have time. It has var x. Oh yeah, part C. Yeah, we'll see if we get to all of that. But what we're trying to look for are the constants A and B. So this question tests you on several things, right? It tests you on whether you understand what a PDF is and also what expectation is. So expectation, you always, like I said, you always refer back to the definition. What's the expected value of a continuous random variable? Well, if it's continuous, it goes from negative infinity to infinity of x, f of x, dx. So that's important. Now, my integral for this particular problem is not going to go from negative infinity to infinity because my function is defined between 0 and 1. So this instead becomes 0 to 1 of x multiplied by a plus b x squared dx. This equals 3/5. They already tell me this. So all I have to do now is just continue on and call this ax, call this bx cubed. Evaluate from 0 to 1 of dx. This equals 3/5. So then you do ax squared antiderivative plus bx to the 4th from 0 to 1 equals 3/5. When you evaluate at 1 and at 0, you get a over 2 plus b over 4 equals 3/5. So what do I have? What's the common factor here that I can multiply this whole thing by? I'll multiply this whole thing by 20. And when I do that, I get 10a plus 5b equals 12. What did I just discover? I discovered an equation with 2 variables. What's the problem behind this? It's an equation with 2 variables. So I would have to need another equation to solve this, wouldn't I? So this first equation was based upon the expected value. How would I get another equation with a's and b's in them? And this is exactly the other piecewise. And this is exactly why I mentioned you have to know what a PDF is. What's a PDF again? What's the requirement for a function to be considered a probability density function? if this is indeed a PDF, the integral must equal 1 when you take it, right? From negative infinity to infinity. This is what it means. So you do the integral from 0 to 1 of a plus bx squared. This has to equal 1. Has to. So this becomes ax plus bx cubed over 3 from 0 to 1. And then look what I get. I get a plus b over 3 equals 1. Multiply the entire thing by 3, and I get 3a plus b equals 3. So look what I have now. I have two equations with two unknowns. Can't I solve this? And then this is another instance where you're like, oh, this is why we study solving systems of equations. Because you may have to use it. Now it's a technique that you use for mathematical reasons, right? So now I can solve for b, multiply the top here by -5, and I'm left with negative 15a minus 5b equals negative 15. This is 10a plus 5b equals 12. You add this and you get negative 5a equals negative 3. So a equals 3/5. And then if a equals 3/5, you can plug it into the first equation. This is 3 times 3/5 plus b equals 3. This is 9/5 plus b equals 3. So b is equal to 3 minus 9/5, which is 15 minus 9 over 5, which is 6/5 b. So my answer is a is 3 over 5, and b is 6 over 5. That is part A. So we were able to figure out the A and B constants of our probability density function. So once I'm able to do that, then I can find part B, right? I would be able to do part B because what does part B ask? The probability that x is less than a half. And what is that? This is equivalent to, from 0 to a half, of 3/5 plus 6/5 x squared. And then we just integrate. This just becomes an integration problem. We know that if we plug in 0, we get 0, so we don't have to worry about the 0. The 3 here becomes a 2, so this becomes 3/5 times a half plus 2/5 times a half cubed. This is 3 over 10 plus 2 over, this is 5 times 1/8. But the 2 here becomes a 1 because you cancel. And so you're left with 3/10 plus 1/20. Multiplies by 2. I get 6/20 plus 1/20, which is 7/20, which would be what, 0.35? So that's the probability that my x is less than a half. So a lot of these continuous random variable problems are reformulated or just become really a integration problem. But now these numbers have more meaning because you're you're finding the probability of a certain random variable attaining a value less than a half in this case. Make sense? Okay, and so then for the last part, for the variance, hopefully that also shouldn't be too bad. We're going to utilize the definition for variance as the expected value of x squared minus the expected value of x, that being squared. But we already know what the expected value of x is, right? We already know they give it to us. It's 3/5. So then the expected value of that, and if you square that, what do you get? So this is in here. So if you square 3/5, what do you get? You get 9/25. So really the only problem I have to deal with is finding what in the world is the expected value of x squared. So the idea, what is the idea? If you have the expected value of a function of a random variable, that's equal to the negative infinity of g of x multiplied by f of x dx. In this case, my g of x is x squared. So this is going to be the integral from negative infinity to infinity of x squared times f of x. But what is f of x? F of x was what? 3/5 plus 6/5 x squared. So this is the integral from 0 to 1 of x squared times 3/5 plus 6/5 x squared dx. Again, integration becomes an integration problem. This becomes from 0 to 1 of 3/5 x squared plus 6/5 x to the 4th dx. The antiderivative, 3/5 x cubed over 3 plus 6/5 x to the 5th over 5 from 0 to 1. This becomes 3 over 5 multiplied by 1 over 3 plus 6 over 5 times 1 over 5. So this becomes the 3's cancel, and I'm left with a 5th plus 6/5 times a 5th. I can factor out the 1/5, and I get 1 plus 6 over 5. This becomes 1 over 5 times 6 over, 5 over 5 plus 6 over 5, which is 11, which is 1 over 5 multiplied by 11 over 5. And the answer is 11/25. That's the expected value of x squared. And so what's the variance? It's the expected value of x squared minus the expected value of x, that quantity squared, which we found was what? 9/25. So this becomes 11/25 minus 9/25, which equals 2/25. Okay. Okay.